Welcome back. This is part 2 of lecture 3, and here I'm going to give you an overview of the Lassos theory. We are working with three issues here, like prediction consistency, estimation consistency, and model selection consistency. Okay, these are the references for any one of you that will be interested in going deeper into that. Okay, so let's start with an overview, and we begin with the simple linear regression. It's a predictive model, so y equals beta naught plus beta prime x plus u. We have a vector of p explanatory variables, of p covariates. U is a zero mean error term, and we are dividing the vector x into two groups, xs and xsc. Xs is a vector with s elements that represent the relevant variables in the model, the important variables. And xsc, which has dimension p minus s, is the vector of irrelevant variables. These irrelevant variables, they have the respective coefficient equal to 0. Okay, so they are not important to describe the relation between y and x. Okay? And we do the same division for the coefficient beta, the vector beta. So we have beta s and beta sc. As we are considering that s is much smaller than t, we are making a bet on sparsity. So although even when p is much larger than t, we have s much smaller than t. So only a very small subset of the variables is relevant. Okay? And as I mentioned before, p grows with the sample size, so p is p of t. And of course, we are going to set that s also is an s of t, so s also grows with the sample size. Okay? Without loss of generality, we assume that beta not 0, the intercept is 0, such that data are demeaned. Okay? We are also going to assume that there is some kind of standardization in the variables, so all the variables are in the same scale. And we are going to work a lot with matrix notation, such that y equal x beta plus u. Okay? The Lasso program can be written in two different forms. We have already seen that in terms of the Lagrangian form of penalized form or the constrained form. And as I mentioned before, these two forms are equivalent. Okay? So we assume that beta naught is the true vector of parameters. Okay? And there are going to be like three types of errors that we will be interested in. The one is the prediction error that we can represent by the square L2 norm of x beta hat minus beta. And why is that? So let's do something here. Let's write the error, okay, as being the y hat, the prediction that we make, minus y. What's that? This is x beta hat minus x beta naught minus u, right? So this is equal to x beta hat minus beta naught minus u. Okay? So if we look into the square norm of this error term, okay, this will be the square norm of x beta naught plus u. Okay. The problem is that this is something that we have nothing to do about. That's the error that belongs to the model. Okay. So what we can work is this thing here, because this involves the estimator of beta hat. So we are going to focus on this component here okay? That's the error that we can make small if beta hat is close to beta naught. So that's why we are going to look into this error here. We may even be interested in taking the expectation of this guy here, okay? The other error that we'll be interested in is the parameter estimation error, okay? These are different quantities, okay? This one here and that one here. So you may think about why we may be interested in that or not in this one. So this is kind of less restrictive in a sense, but it has a lot of practical importance, because if we are using the model to make predictions, maybe our coefficients are not exactly equal to the true ones, our estimates, but our predictions can be as good as like the Oracle prediction, the prediction that we make when if we knew the truth, if we knew beta naught, okay? Here it's much more ambitious because we want to learn exactly the true parameter. We want to learn beta naught. So this is a more difficult problem. And we are going to see that when we want to, basically what we want to do, we want to put some bounds. We want to show that this is smaller than something that will depend on the sample size and other things. The same thing here. Let's say f prime, not a function, they are not the same, okay? And we want this to go to 0 as the sample size increases, okay? We want this to get smaller and smaller and smaller as the sample size increases, okay? We are going to see that to prove a bound for this error here, we will need stricter assumptions than if we are only interested in this component here, okay? And the third error is even more difficult because that's the model selection error. We want that the support of beta hat, the variables that we include as relevant, that we say, oh, these are the relevant variables, are really the true relevant variables. So we want the support of beta hat to be equal to the support of beta. So we want to bound the probability of this event. In fact, we want this probability to converge to 1 as the sample size increases. And then we are going to see that we are going to need even stricter conditions to prove that. So this is kind of, that's in an ordering sequence. This is the, let's say, the less difficult endeavor. Then it's kind of middle terms, and this is kind of the most difficult one. Okay? We are going to need a lot of assumptions to prove this thing. Okay? So let's go to estimation and prediction consistency, and to understand, to gain intuition on the results for the lasso, let's go back and look into the basic linear regression setup when p is less than t, such that we can use OLS, okay? So we don't need to use any penalization, any regularization. So we're going to make some assumptions. The first assumption is linearity. So we're assuming that the true model is in fact linear, as such that the expected value of y given x is x prime beta naught. So we have the model correctly specified. This, the conditional mean is correctly specified. This can be a quite strong assumption, but let's keep it like this for now, because we need to, as I mentioned, we want to understand the basics. So we are going to relax this assumption later in this course, but now let's think that linearity is a good assumption, okay? And then we can make either one of two conditions here. We can either assume that y and x form a sequence of IID random variables, okay? And x and u are independent, okay? Or y and u is a sequence of IID random variables, and x is fixed in repeated samples, okay? And in matrix notation, we are going to consider that x prime x is full column rank, so the rank of x prime x is p, such that the OLS estimator is well defined, so beta hat is x prime x minus 1 x prime y, okay? And with that, we have some facts. First fact, that under the above assumptions, the expected value of the prediction given x is x beta naught. And this comes from the fact that the OLS estimator is unbiased, okay? So if under the assumption of that all the data is IID and x and u are independent, or assuming x fixed and u IID, we can show that the OLS estimator is an unbiased to the true parameter, okay? And the in-sample prediction we can write in this neat matrix form. That will be like y hat is equal to a projection matrix px y. Remember that px, a projection matrix, is idempotent, so px times px is px. So this will be useful for us later, okay? And the out of sample prediction, which means that I observe a new point, a point that was not used to compute beta hat. And what's the prediction for this new point? Will be x naught prime times beta hat. So that's exactly what we have here, because this is beta hat. Okay? All right, so in the OLS case, it's pretty easy to show that the 1 over t, the expectation of the square L2 norm condition on x, okay, this will be equal to 1 over t, the trace of the covariance of x beta hat given x. Why is that? Because look at this. This looks like a variance term, right? Because we have a random variable here, x beta hat, that we know that the condition expectation of x beta hat is x beta naught. Okay? Okay? So this is kind of the random variable minus its mean, and what's the L2 norm? Is the sum, okay, of the variance elements of this big covariance matrix, okay? So we want just the diagonal of this conditional covariance matrix so that we have the trace here, okay? But what's the covariance of x beta hat given x? So x is not random because we are conditional on x. So this is basically the trace of the projection matrix px, sigma square identity px. So we can put this sigma square here and put px here. Why we can do that? Because we are working with the trace. So the trace is a number, so we can work with that. But because of this is a projection matrix, this is just px. Okay? So when we do that, we have that this is just sigma square p over t. So basically, we say that the expected value of the prediction error, the conditional prediction error for an OLS regression, okay, is just sigma square p over t. So it goes to 0 with t, okay? And of course, the problem, the error, this bound is larger, the larger is p. So when we have a lot of variables, of course, the problem is more difficult. But remember, we are in this setup here, in fact, where p is less than t. Okay, so we are considering that p is fixed. So as t goes to infinity, this thing here goes to 0 as t goes to infinity. Okay? We can use the law of iterated expectations to compute the unconditional expectation, right? And we can also do the same thing to the out-of-sample prediction. Remember that, or see here that we have this new point x naught, so we can show that this will be given by sigma squared, the trace of the product of these two expectations, and we can bound that, by the, this will be larger than, we lower bound it, than sigma squared, the trace of sigma minus 1 t, where sigma is the covariance matrix of the predictors, which exactly this bound here. So we show that the out-of-sample prediction error will have a larger L2 norm than the in-sample prediction error. So the out-of-sample risk is larger, equal or greater than the in-sample risk. And this is kind of natural, because this is a new point that we had never seen before when we were conducting the estimation. Of course, we can not, to derive exact results, the exact bound, we will need the distribution of the regressors, right? Because that makes no sense in this case to assume that the regressor is fixed. So we assume that it's random, so we will need to make assumptions on the distribution in order to compute these expectations here. In case of Gaussianity, we can derive this bound, and we can show that will be larger than the in-sample one, okay? But only in the very specific case of Gaussian random variables. Now let's move for the lasso, and now, when P is larger than T, okay? And let's consider the constrained version of the lasso. Okay? In this case, we are going to set the threshold to be exactly equal to the L1 norm of the true parameter, beta naught, okay? So this is kind of the optimal solution, because it's the exactly right amount of shrinkage that we have to include in order to make beta naught feasible to the lasso program. Okay, so that's exactly the correct amount of shrinkage, because we are assuming that we know here the truth. Okay, of course this is not feasible in practice, but I just want to show you. Okay, if we knew that, what can we say about the risk and the prediction error of the lasso estimator in high dimension, in true high dimension setups. Okay? So due to optimality of beta hat, we can write that the cost function, remember the cost function that we are optimizing is the L2 norm of the error, okay, the squared L2 norm of the error. So when we evaluate this at beta hat, this will be less or equal than the cost function evaluated at the true coefficient beta naught, okay? Because beta hat is the optimal solution to the lasso program. Okay? After some algebra, in the extra slides for theory, I do it step by step, okay? If you are interested, but we can show that simple algebra that the prediction error, the squared of the L2 norm, is less or equal than the estimation error times this random term here, that's x prime u. Okay? But we can bound this term on the right-hand side. We are going to use Holder's inequality. Okay? So with Holder's inequality, we can say that the right-hand side, the left-hand side is bounded by the infinite norm of x prime u times the L1 norm of the estimation error. Okay? We are going to use this condition a little bit later, okay? But because we just assuming that the columns are normalized, okay? So to achieve this result, we don't need this condition. We are going to use it later. Okay? So now, because we have that, remember that the lasso program implies that the coefficient should be less or equal than C. So the lasso solution, the estimator, beta hat, should be, the L1 norm should be less or equal than C, but we set C to be the L1 norm of beta naught. So we can have here a very crude bound and say that, okay, this is bounded by 2 times the L1 norm of beta naught. So we have this bound here that our prediction error, the L2 norm squared of the prediction error, is less or equal than 4 times the infinite norm of this random term here that depends on these unobservable errors, okay, times the L1 norm of the true coefficients. This thing here, we can give an interpretation for that. This is related to the sparsity, right? Because that's, remember, that's exactly the quantity that we are shrinking. So that's the true shrinking, the true sparsity in the nature for this problem. That's the L1 norm of the coefficient. Okay? So this is okay, but this thing here, it's difficult to give an interpretation for that. We don't know exactly what this means. So we want to simplify this expression a little bit further. Okay? The problem that to do this, we have to try to compute this infinity norm here. So there are many ways to handle this problem. Okay? And if you look at different books, they can give you different solutions to the problem. Okay? What I'm going to do here, okay, bear in mind that we are in this setup where we are working with the constrained version. So what I'm going to do is that I'm going to make assumptions about the distribution of the error, okay? And I'm going to assume that X is fixed. So once I tell you that X is fixed, okay, the error term follows a distribution that in our case, guess what? It will be the Gaussian one, because this is the easiest one to work on. So an assumption about implying that U is Gaussian, X is fixed, and column Y is bounded. Then we can use a well-known probability inequality to say that this number will be less or equal a bound with high probability. So we want to look at which is the threshold that I can put here, what's the bound that I can put here that I guarantee that will be true with high probability. Take into account the randomness of this thing here. This is a random variable. Okay? But what's the source of the randomness? Is this U here. So that's the simplest way to look into the problem. See? So far we don't have like rocket science math here. It's pretty much linear algebra and some inequalities. Okay? So here we are going to need some what we call concentration inequality. Is that maximal inequality for Gaussians. Okay? But it's very simple. So when things get complicated, of course, if you want to relax the Gaussianity assumption on U, if you want to relax the assumption that X is Gaussian, if you want to introduce dependence on the axis, so then things start to get a little bit uglier, okay? And the bounds will be uglier. Okay? But so far we want to understand what's going on, so I'm going to keep things simple, okay? And now as we move forward, we can discuss more complicated situations. Okay? So as I mentioned, we need this assumption. So whenever this is the case, we can show that the expected value of the square L2 norm will be bounded by the sparsity and a term that's the square root log p over t. And why this is good? So first thing that you have to bear in mind, that as compared to the OLS, we have a square root t here and not t. So the convergence rate, the rate that converges to 0, is much lower than in the case of OLS, because we have this t here. Okay? We also have this extra component here that's due to the sparsity. Okay? We are in the high dimension, so we have to pay a price. Okay? So the larger is the L1 norm of the true coefficients, okay, the larger will be the bound. But there's one thing that here is interesting. Remember that P is P of t, okay? So, and we want this quantity here. Let's keep this guy here fixed or bounded in a way. It does not grow with the sample size, okay? So this rate, this square root here, grows with the sample size. Okay, both numerator and denominator grow with the sample size. But what we want that when t diverges, we want this quantity here to converge to 0. Okay? To achieve that, what do you need? We need that t grows faster than log p. So we need log p to grow slower than t, but there's this logarithm term here. So in fact, p can grow exponentially fast. So we can have really an extremely large set of variables. So p can be exponentially larger than t, because we just require that log p over t goes to 0. So there's a lot of flexibility. Of course, this log term here comes from the assumption that u is Gaussian. What you are going to see if you are interested and you go deeper into the theory is that when we relax this assumption here, we have to say something about moments, the expectation of moments. It should be bounded of u. Okay? Because remember, the Gaussian distribution, you have all the moments bounded. Okay? And like the Cauchy distribution, you don't have any moment. Okay? So if you are in somewhere between, depending on the number you have here, you have to impose restrictions. What's going to happen is that this logarithm term here will become a polynomial. So instead of having like exponential growth, you can have polynomial growth. Okay? And depending on how many moments do you have, you can have a polynomial growth that's faster than t or slower than t. Okay? And depends how flexible is the model. But that's the big picture. Okay? We can derive the same thing for the Lagrangian form. So if we put kind of a bound on lambda, that's log p divided by t. E is just the exponential of 1. Delta is a small number. So we can say that this is, we achieve exactly the same bound. The constants that we are going to have here will be different, but the bounds are the same. Okay? So basically, what we say in this case is that we found a bound to that term here that will hold with high probability. Okay? And then that's the trick to construct these bounds that we have here, right? If you want a full derivation of these results, take a look into the extra slides for theory. There I describe step by step how we get to this result. Okay? These bounds are known as the slow rates. Okay? Can we improve on that? Yes, we can. But we have to impose more restrictions. So if we impose now more restrictions, we not only will be able to improve these bounds, okay, but also construct a bound, derive a bound for our second error term when we are just looking into the estimation error. So beta hat minus beta naught. But we need something more. Okay, so remember that here's kind of the least we have to assume that's what we can reach this result that you see on your screens. Okay, but if we want to more flexible bounds, basically what we need to control the correlation among the covariates. Here, so far we haven't said anything about correlation among the variables. So now we have to say something, okay? And what's the idea? Okay, imagine that you have a cost function, okay? Imagine that you have a cost function that I call Q of a parameter beta that we want to minimize, and here's the parameter beta. Okay? Imagine that this cost function varies with beta this way. Okay? So changes, if you have one beta here and another beta here, small changes in beta will induce also small changes in Q. Large changes in beta will make large changes in Q. Why is that? Because this function, there's a lot of curvature. Okay? Remember, but have another situation here, same thing, but you have a function like this. So you may have like differences in two betas that will introduce almost no differences in your function Q. So you have almost flat situation. Okay? So this is related to the convexity of Q. Basically, we are talking about strong convexity of Q. So, and this is related to the Hessian of this function Q. So basically, we don't want flat surface, we want curved surface. In a regular optimization problem, like in a linear regression, basically what you need is you need that the minimum eigenvalue of this matrix to be bounded away from zero, be larger than a sigma, and the sigma will be larger than zero. So the further away it's from zero, the more curvature you have. Okay? However, this won't be achievable for large dimensions. Why? Because by construction, this Hessian here of our cost function, in our case, will be related to x prime x over t. But in large dimension, x prime x over t is singular. So the minimum eigenvalue of this matrix is zero. So it's not strong convex. But what we can do is that maybe it's not curved in all the directions. If I take a piece of paper here, it's completely flat, right? But I can make it curve in one direction. Okay, if I look here to here, it's curved. But if I look here in this direction, it's completely flat. So the idea is that instead of having a full flat cost function, we are going to have some curvature, but only in some directions. Okay? During our live session, I'm going to show some simulations about that. But which are these directions? Well, a good result that if we have sparsity, sparsity induces a kind of conic region. That's basically the error we make for the parameters that are related to the irrelevant variable. So the beta hat SC minus beta SC naught, okay, is less or equal than 3 times the L1 norm of the errors we make for the relevant variables. So this induces a cone. Okay? Because this is a relation between the betas. So we know that the lasso solution lies in that region. So as it lies in that region, we don't care about the cost function outside that region. We just care about the cost function within that region. So we want to impose curvature in this region. So we want to restrict that when we do a transformation, that we transform the covariance matrix x prime x over t. In these regions, we may have like this bounded, the eigenvalues bounded away from 0. So this translates into a condition that's called the restricted eigenvalue condition. So if we take any vector, beta, that belongs to that conic region, okay, and for this beta, the covariance matrix, that's what's this thing here? Is exactly del 2 norm squared of x beta divided by t. If this is larger than a constant, that's called the compatibility constant. If it's larger than the L2 norm of beta, then we have this restricted eigenvalue condition. Okay? So this looks much artificial, but the idea is pretty clear that we want, what we are forcing, that in the directions induced by this with this vector beta that belong to any vector that belongs to that conic region, we need the cost function to have curvature. So we need some properties on the Hessian of our cost function. Okay? So the question is, which kind of data satisfy these restricted eigenvalue conditions? There's a lot of papers showing that. Basically, Gaussian variables, IID Gaussian variables will, this condition will hold. For sub-Gaussian variable, this condition will hold. For some other sort of variables, we have to impose additional conditions, but it's possible to show that this restricted eigenvalue condition holds. So it's kind of a wide class of design matrix X will satisfy the restricted eigenvalue condition. Okay? And this is basically the picture I have I draw on the slides. Okay? So we want something that we make small changes on the parameters beta. These will induce proportional changes on the cost function. We don't want flatness. We want something that's really curved. Okay? So if this is the case, we can show that the prediction error is bounded by something that's the ratio of log p over t. So this is the fast rate. So we can almost recover what we have for OLS, but now we have this log term here, and we have this S naught here, the sparsity. Okay, so that's the price to pay. That's our price to pay for working on high dimensions. And again, we have this log term here, so P can grow exponentially fast. So if we impose restrictions on X, we have much faster rates. Okay, and we can also derive bounds on the estimation error. So, but here you look that the boundaries are stricter than the ones here. And why is that? Because this is a more difficult problem than that one. Okay? So that explains why we have a square root t here. Okay? But they are somehow very similar, right? So if you want to look the derivations of these results, you can take a look on our on the slides for the theory of lasso. So to wrap up, let's look into model selection consistency. Okay? So now what we want, we know what is estimation consistency, is to get the beta hat equal to beta naught. Okay? But what's model selection consistency? We want to select the right variable. So we want to estimate as non-zero the same coefficients as the truth. Okay? And we may want something that's even more difficult, that's sign consistency, because for the ones that we estimate as different than zero, we want to get the sign correct. So if it's a true negative parameter, we want to estimate it as a negative parameter. If it's positive, we want to estimate as a positive parameter, right? And we say that the lasso will be strongly sign consistent if the limit of the probability of a beta hat equals in sign to beta, so the sign function of beta hat is equal to the sign function of beta naught, if this probability equals to 1 in the limit, or general sign consistency, that we say that there is a lambda that will make this probability converges to 1. Okay? So strong sign consistency implies general sign consistency, and basically the strong version implies one can use a pre-selected lambda to achieve consistent model selection, and the general alternative says that for a random realization there exists the correct amount of regularization that will give that will deliver the true model. Okay, so we want this. So we want to have a correct model selection. So we need something more, something that's stricter than the restricted eigenvalue. Okay, a stronger condition. And which condition is that? Is the irrepresentable condition. Okay, which translates into these bounds here. So what's sigma SS? Is xs prime xs divided by t. Okay, sigma sc is the same thing for sc divided by t, and of course scs is xc prime xs divided by t. Okay, so what does this mean? This is equivalent if we have something that if we take the regressors, the irrelevant regressors, if we write it as a regression on the relevant regressors plus an error term, okay, what's delta hat? Delta hat is exactly this term here. There's a hat over here, right? See that we are using sample counterparts. So this is exactly the OLS coefficient of a regression of the irrelevant variables on the relevant ones. And basically what we are saying that all these coefficients should be very, very small. So what does it mean to have, does it mean a coefficient that, OLS estimator coefficient that's very, very small? That we are bounding the correlation among the irrelevant variables and the relevant ones. So either we consider that no correlation, because this is too small, or if there is correlation among relevant and irrelevant variables, it should be a very structured correlation, such a way that these theta parameters are pretty small. Okay, so we are kind of bounding this amount of correlation. So this is the translation for this condition with this weird name, like the weak representable condition. But basically, it's take the relevant variables, take the irrelevant ones. You want that the correlation between them are pretty small. We don't care about the correlation within each group, but in between the groups, that's the important one here. Okay? And we can use that. How do we derive these conditions? Basically, we show that if the strong irrepresentable condition holds, okay, the probability of our estimator beta hat being sign equivalent to beta naught will be large than the probability of two events, and the events are these two ones here. So what we want to make this pretty high. Okay? So basically these events, they translate into one part is I want to include the model the correct variables. The correct variables should be included in the model. Okay? And the irrelevant variable should be excluded in the model. So when I have the intersection of both, I correctly include all the variables and I correctly exclude all the irrelevant variables, then I have model selection consistency. So AT implies that the signs of beta S are estimated correctly. So given the event AT, the event beta further imply that the estimates of the irrelevant variables will be shrunk to zero. Okay? And the penalty term will kind of trade off these two events. Okay? Smaller lambda, larger A, but smaller B. Okay? Lasso will pick more irrelevant variables. On the other hand, the eta parameter that we have here, which is related to the strongly representable condition, okay? It will lead to larger B and have no impact on A. So there's this trade-off. Okay, so that is under which conditions we can make this probability large enough. Okay? And basically, there are two setups. One setup is the low dimension case. So basically, we need some bounds on the design matrix. That's this condition. These are kind of some regularity conditions. Okay? And if this is the case, then basically in low dimensions, once you have the strong irrepresentable condition, you get a perfect model selection with probability that will be large. Of course, this will depend also on these parameters that's related to the choice of lambda. Okay, but basically what I'm saying is that with fixed P, S, and beta naught, the strong representable condition will give you model selection consistency. Okay? And if you are interested in the all the derivations are in this paper by Zhao and Yu. It's also in our Google folder. Okay? And this is just a follow-up theorem, but this one is the interest one. Large PNS. Okay? So for large PNS, there's an extra layer of complication. Okay? Not only we're going to need the representable condition, but we are going to need this thing here. So pay careful attention about that. That's called the beta min condition. What's basically saying is that for all the relevant variables, okay, remember it's the relevant set, the absolute value of the true parameter should be larger than a constant. Of course, this is bounded, it's normalized by the sample size, but basically saying we cannot deal with small coefficients, right? So for Lasso to make correct model selection in large dimensions, large PNS, we need the representable condition, plus beta min condition. This is pretty strong. So if you have small coefficients, you cannot distinguish it from zero. Basically, that's what I'm saying. Okay? So if we have that, then all these theorems, what they say is that you can get model selection consistency. Okay? So from all these letters and numbers and theorems, what you have to keep in mind is, for prediction consistency, it's low rates, almost no assumption. Okay? For prediction consistency, fast rates, we need curvature of the cost function, okay, in some directions, restricted eigenvalue. Also, we need this restricted eigenvalue to compute bounds for the estimation error. What's the restricted eigenvalue? We have to bound somehow the correlation among the variables. Okay? But still, we can deal with correlated variables. But it cannot be like, we cannot have like perfect multicollinearity. Okay? But now if we want to do model selection, pick the right variables, then we need something that's stronger than the restricted eigenvalue. That's the representable condition. And we need the representable condition, and we also need that all non-zero coefficients to be larger than a minimum. Okay? Usually this is something of the order of 1 over square root of t, the sample size. So everything that's below 1 of square root of t, usually it will be set to 0. Okay? And finally, when the representable condition holds, of course, if you have like constant positive correlation, then it's okay, representable condition holds. When you have bounded correlation, it also holds. When you have power decay, it also holds. There are many other situations where the representable condition holds. It's not to say that you need the regressors not to be correlated, but if you have correlation between irrelevant and relevant regressors, this correlation should be structured in several ways. I give 3 examples here. There are many others. Okay? Let me finish with an example. I have a linear model here, okay? And x3 depends on x1, on x2, and on vt. Okay? This 1/3 here does not exist. Okay? And I have two situations. Beta 1 equals to 2, beta 2 equals to 3, beta 1 equals to minus 2, beta 2 equals to 3. In one case, the strong representable condition fails, this case here. And in the other one, the strong representable condition holds. Let's see if Lasso can select the true variables, that would be 1 and 2. So in the first case, you see that Lasso, as we increase the lambda, Lasso picks beta 2, 1 and 2 as the relevant variables. 3 is selected only when we have like very large lambda, 3, very small lambda, sorry, 3 is not selected. So here we are kind of decreasing lambda, increasing the L1 norm, so we are decreasing lambda. So when lambda is very large, we do not select anything. So we are decreasing lambda, then we start selecting 3 and 2, and then we select 3, 2, and 1, and then when we have almost no penalty, then OLS is kicking in, and then we pick 1 and 2. On the other hand, if the representable condition holds, you see that 3 is never selected, and we select 1 and 2, so we are doing the correct model selection. Okay? So this is for today. And for this second block, we have 2 more blocks to go. Thank you.